Welcome to 6-7 video lesson in Algebra 2. The concept that we're going to talk about today is inverse relations and functions. And there are 7 boxes, so let's dive into box 1 right away. So box 1 says, I want you to remember what a relation is. And a relation is nothing more than an ordered pair. So when you have an x and a y together, you have a relation. So as an example, I have this relation over here. I have the pair 1, 2, I have the 0.57, and then I have the 0.39. And collectively, this set of ordered pairs makes a relation. And the thing that I wanted to move forward with you on this is that we can then pull from the relation the domain and the range. Now the domain is simply going to be all of the x values in the relation. So the domain would be something like 1, 5, and 3. And the range, of course, would be all of the y values in the relation. So 2, 7, and 9. So 2, 7, and then 9. And this thing that we can use is called a mapping diagram. So what that means is that if you give me a 1, 1 is going to map to 2. If you give me a 5, 5 is going to map to 7. And if you give me a 3, then 3 is going to give back and map to 9. So we can use a mapping diagram to visualize a relation, and a relation is nothing more than an ordered pair. So this should be a review, so I wanted to bring that to your attention. In box number 2, we're going to talk about finding the inverse to a relation. So check it out over here. So I've got x's and I've got y's. So I've got a domain. These are all the members of my domain, 0, 2, 3, and 4. And then these are all the members of the range, -1, 0, 2, and 3. So if I was interested in the inverse of this relation, well, what I would do is I would switch the x values for the y values. So instead of having 0, -1, I would have -1, 0. And instead of having 2, 0, I would have 0, 2. And instead of 3, 2, I would have 2, 3. And instead of 4, 3, I would have 3, 4. So if I wanted to talk about the inverse relation, all of my x's and my y's would be switched. So I'd have -1, 0, 2, and a 3. And then my y's would be 0, 2, 3, and then 4. So you'll notice that all of the x's became all of the y's, and all of the y's became all of the x's. So finding the inverse is pretty straightforward. All we have to do is switch the x for the y. Okay, box 3 is sort of a visualization of box 2. So what I have here is I have a relation for you, and then I've graphed that relation. So notice I have the point -3, 1 graphed for you right there, -2, 4 up there, and then 3, 5. If I wanted to take a look at the inverse relation, first I would switch all my x's and y's. So I'd have a 1, a 4, and a 5. And then my y's would be all my x's, so there'd be -3, -2, and then a 3. And then I'm going to go ahead and graph these in red for you. So instead of -3, 1, I'm going to have 1, -3. So 1, -3 ends up being down there. 4, -2 ends up being right here. And then 5, 3 ends up being right there. So you can see that there is a mirroring effect going on. Or hopefully you can see that. If I were to draw this diagonal line right here, draw this diagonal line right down here, okay, you would see that there is an equal distance away from this diagonal line. It's a pretty cool property. So this tells us something about how to graph relations, and there should be a symmetry to all of graphs that are the graphs of relations and their inverses. Okay, box 4 is a U-try. Go ahead and find the inverse relation to the one shown. X's and y's. X has a domain of 0, 5, 6, and 3. Y has a range of 1, 4, 7, and 9. Tell me what the inverse is going to be. Okay, hopefully you got the right answer. The inverse relation is just 1, 4, 7, and 9 in my domain, and 0, 5, 6, and 3 in my range. Okay, in box 5, what we're going to do is we're going to actually apply this logic to an equation. So let's say I have an equation of a line that says y is equal to 3x plus 5. And what I'm interested in is the equation for the inverse. So the first thing that I'm going to want to do is I'm going to switch the x and the y variables. So now I'm going to have this. I would have an x is equal to 3y plus 5. And all I have to do now is resolve this equation for y. So I'm going to subtract 5 from both sides. I'm going to get x minus 5 is now equal to 3y. And then I'm going to divide by the number 3 on both sides. So I get x minus 5, all quantity divided by 3 is equal to y. So this is an equation that represents the inverse to our original problem here. So x minus 5 over 3 equals y. That's my inverse equation. Box 6 is another example of graphing a relation and its inverse. So in the blue cloud, I have for you y equals x squared minus 1, which I'll graph on the coordinate plane in blue for you. This, of course, is a parabola where the vertex is down at 0, 1, and then it's moved up, and then over 2, up 4, and so on and so forth. So it's going to look like this right here. This would be my the blue equation, or the equation in the blue cloud rather, okay? And then this one, okay, the square root of x plus 1, well, if I take each of those points and I do, this is the inverse, by the way, this one is the inverse, that's kind of given to you. If I take plus or minus the square root of x plus 1, I would have this graph going on. So in red, this one, and then 2, and then so whatever these are, 1, 2, 1, 2, 3, 4, and then this one down here. So I would have this graph in red going on. And they would still, the reason I know that is because they still mirror across this point, oh shoot, sorry, this one over here, across this line. So let's get rid of these for you. And back this way as well. So these, if I draw those correctly, right? So you can kind of see that each point is the same oh shoot, this part's wrong. Hold on, team. Okay, so in this box 6, we're going to graph a relation and its inverse. So the one in the blue cloud here is x squared minus 1, and its inverse relation equation has been given to you, plus or minus the square root of an x plus 1. So I'm going to go ahead, since this is the one that I'm familiar with, I'm going to go ahead and graph this one in blue for you. That's a parabola with its vertex down at 1. So we should be pretty good at graphing this one with no problems. And I would see this going on, and then I would see this going on. Okay, now remember that the graph and its relation is reflected over the line, this main diagonal here, y equals x. So I'm going to go ahead and put that in really quick for us, and then try my best to get it as straight as I can. And then now I'm going to take each one of these points, and I'm going to mirror it over the line. So it looks like this point is actually on the line, right? This one's going to be here, and then I would have something that's looking like this. Or sorry, this one should be, what did you wrong here? Oh, this one should be here. There we go. So then I would have this graph in the red, and then it'd be coming down this way as well. So the whole point of this is to show you that a graph and its relation can be mirrored over the x-axis, or over the line, sorry, y is equal to x, the main diagonal, and you get this beautiful symmetry about it. So this was what box number 6 was all about for you. Okay, lastly in box 7, we're going to consider the function f of x equals the positive square root of an x minus 2. So I'm going to start by plugging a few points in and making a sketch. So if I plug in a 2 for this function, 2 minus 2 is 0, and the square root of 0 is 0. So I know that 2, 0 is a point on the graph. If I plug in a 3, 3 minus 2 is 1, square root of 1 is 1. So 3, 1 is on the graph. And then of course if I plug in a 6, 6 minus 2 is 4, and the positive square root of 4 is the number 2. So I'd have this graph right here. So here's a quick little sketch right there, okay? Now from here, I could see that my domain would be all real numbers x, such that x is strictly greater than or equal to the number 2, because it could be 2. So all my x values begin at 2 and they move to the right. The range, it would be all real y's, such that y is greater than or equal to 0, since it starts at 0 and then moves up. So let's find the inverse function for this, okay? So here's what I have. I have f of x is equal to the positive square root of x minus 2, all right? I'm going to change f of x equal to y, so that I could see that this is equal to, y is now equal to the square root of x minus 2. since f of x and y are related. Then I'm going to do the trick where I switch the x and the y. So x is now going to be the square root of y minus 2. And then I'm going to resolve this for y. So I'm going to square both sides. So I get x squared is now equal to y minus 2. And then solve for y. So I get y is now equal to x squared and then a plus 2. And you guys, ladies and gentlemen, this is the inverse function, and the name that we give to the inverse function is f inverse of x. So f inverse of x now is going to be x squared plus 2. So what that does is if I was to graph that, that would just be a parabola that is moved up 2 units and looks like this. And then of course, if I did the other side, then I would get something that looks like that. And this graph is mirrored across the axis of y is equal to x. So now we just give a name to this, and that name is called f inverse of x, and we can move on into inverse functions. And that was the whole point of box number 7. And in addition, you should also realize that the domain and the range have now also switched. So the domain for the my new function here is everything that's bigger than 0. And oh yeah, because I just have this side here. The domain is everything that's bigger than 0, and then the range is everything that's greater than 2. So as a consequence for inverse functions, what you'll notice is that the domains and the range also switch. We're going to talk more about this in class.